Hi, in this video we will cover how to determine half-life values from SLAM-seq data. I will walk you through the 4 necessary steps to go from raw data to calculating mRNA half-lives. Alright, let's dive into the first step, downloading and setting up your data. Today we will be using data from the original SLAM-seq publication. So this is the original publication, and we will go and access the data by clicking here the accession codes. This takes us to the gene expression omnibus data, and we will be using the ESC's data wild type samples. Is this one over here. So if we click there, we have here the different samples. We will not be using all of them, we will be using some of them. And where we access the data, I like it to get it from SRA. So you go to run, and then you go to download the FASTA, and we ask the fastq, and that will start downloading our data from this 1-hour chase. And we get the rest of the samples in a similar way. Next, we'll download the genomic FASTA file from the UCSC genome browser. To do that, we go to the UCSC genome browser, then we go to downloads, genome data, and mouse genome. You can download the whole genome. For this example, I will just download chromosome 1. This doesn't make a difference. I don't want to align the whole genome, so I want just to give an example. That's why I'm doing it with chromosome 1. Finally, we download the bed file containing the position of each gene. To do this, we also go to genome browser, but here we go to tools, table browser, and then we go to the same genome that we were downloading. In this case is the MM39, and we will be requesting the bed files only for chromosome 1. And we go get the output, and we say get the bed. And that's how we get the bed file. Now that we have the raw fastq data, the genomic FASTA data, and the bed file with the genome annotations, we are ready to launch the first step of the pipeline. If you need a refresher on the different types of bioinformatics files, check out one of my previous videos. Just click the link on the screen. So the way that we are going to organize the data is to put it in this folder named data, and we will have here all the fastq file for the different samples and time points. And we will put here the genomic data and the annotation data. The second step of the pipeline is to run the Slamdunk Nextflow pipeline to generate conversion values, which will be used to calculate the half-life of the transcripts. So to download the code, we go to this GitHub repo, tnewman Slamdunk, and we ask for the code. We download the whole stuff. So, and we create then this NS SLAM-seq data, which has all of the code that we'll need for our analysis. Next, we generate the metadata for our experiments. I have it here in this sample info final, and we will be having only one condition, one type. We will do in ESCs. Here is the name of each of the files. This is the name of each of the conditions. This is the type of condition, is always chase, and this is the different time points we are looking here, which selected 0, 3, 6, and 12. Once we have everything in place, we run this line of code to trigger the Nextflow run with our NF SLAM-seq scripts that we just downloaded, and the metadata that I show you together with the genomic data and annotation data. So that will run and will generate different files, and these are the files that we are going to use for our analysis. These files contain the conversion rate or mutation rate that we will use to feed the decay model to estimate the half-life of the transcript. If you are interested in a more detailed walkthrough of this step, I have a dedicated video on it. Check it out using also the link that is now on screen. The fourth step is to prepare the data that we will need for our model to calculate the half-life values. First, we download some additional annotation data to assign gene names to transcript. We will use biomaRt, and we will use the ensembl biomaRt. We are working with mouse, so we will go and use the mus musculus gene ensemble. mart, and at this point we request the symbols and this ensemble transcript ID, and we will save that. Next, we combine all the data from the different samples, keeping the conversion rates, transcript names, and chase time. We will combine the data from those files that the Nextflow data pipeline generated, and we are going to make use of the metadata to compile everything, and we don't have to write anything again. Here we are putting all the conversion values from all samples in one table. The next thing that we are going to do is to add the metadata to that full table that we just merged. We are going to incorporate also the symbol data, and with that we download the data and then we do the merging. So the final thing that we are going to do is to normalize our conversion rates so that the first time point times 0 will be 1 and the rest will be normalized accordingly. And with that, we do that with this pipe here. So for example, this is the normalized value for this ZP3 receptor gene. We have the values at time 0 being around 1, then values go a little bit down, and at 6 hours further down, and at by 12 they are very close to 0.1. So that's our normalized data. So the resultant table will be used to feed our model. The fourth and final step is to feed an exponential decay model to the data and infer from there the half-life of the transcript. To do that, we are going to use the purrr library, and we are going to upload the data, normalized data that we generated. We are going to nest the data so that we can hand this to purrr with this nest function here. So here we have for each gene this variable. For example, we have this kr4, and in this variable this is itself a data frame where we have the 3 different time points and their normalized values. So for this table, what we have is for values 0, 3, 6, and 12, how much is that conversion value. Like, since we normalize everything for time 0, that value is around 1, and then this decays for the different 3 values that we have at the other 3 different time points. So and these are the values that are in this plot that I'm showing you. So this is the actual function that we are going to test. We are going to say that normalized value falls in an exponential way depending to the time. In other words, we are going to use this equation here. The abundance depending to the time equals to the initial abundance times e to the minus kt. Then we use this function to calculate actually the half-life from that k number. That will be this number over here. How to get there is not very complicated. You have to follow this reasoning here, and this is what we get, and that's what we have over here, and that's what we are going to fit. So once we get that, we have our final for each value, the half-life, and this r that we calculated is an estimation of how much the points deviate from the fit. So ideally this should be small. We've been using around 0.6, and that works pretty well. So now that you have the data, you might want to plot and visualize it in different ways. For guidance on that, check my next video, and I will see you there.